At the heart of modern physics lies a paradox. We have two magnificent theories: general relativity, which describes the grand architecture of the cosmos, and quantum mechanics, which governs the strange and unpredictable world of the subatomic. Each has been tested to extraordinary precision. Each has revolutionized our understanding. But when we try to merge them, to describe gravity in quantum terms, everything breaks. Welcome back to Infinity Beyond. In this episode, we face the biggest challenge in all of science: the quest for quantum gravity, a theory that can unify the very large and the very small into a single, elegant framework. General relativity tells us that gravity is not a force, but the curvature of space-time caused by mass and energy. It predicts black holes, gravitational waves, and the expanding universe. Quantum mechanics, on the other hand, describes particles and fields in terms of probability waves, superposition, and entanglement. It governs the behavior of electrons, atoms, and photons with astonishing accuracy. But combine them, you get infinities, equations that spiral out of control, predictions that defy physical meaning. This fundamental incompatibility has haunted physicists for decades. To understand the earliest moments of the Big Bang, or the interior of a black hole, we need a theory that blends quantum effects with gravitational curvature. That's what we call a theory of everything. One of the most ambitious contenders is string theory. String theory proposes that the fundamental units of nature are not point particles, but tiny one-dimensional strings, vibrating at different frequencies. Each vibration gives rise to a different particle. These strings are unimaginably small, on the order of the Planck length, 10^35 meters. String theory naturally includes gravity, through a particle called the graviton, a quantum of the gravitational field. But it also demands extra dimensions, typically 10 or 11 total, with most of them compactified in curled-up spaces like Calabi-Yau manifolds. While beautiful mathematically, string theory remains untested. No experimental evidence for supersymmetric particles, no confirmation of extra dimensions, no direct proof of strings. Still, it offers a coherent framework where quantum mechanics and gravity coexist peacefully. Another contender is loop quantum gravity, LLQG. This theory takes a different approach. Instead of positing new particles or dimensions, it attempts to quantize space-time itself. According to LQG, space is not continuous. It's made of tiny, discrete units, like atoms of geometry, connected in loops. In this view, space-time is woven from a quantum network, and gravity emerges from the way these loops interact. Loop quantum gravity has had some success in explaining aspects of black hole entropy and the early universe. It doesn't require strings or extra dimensions. But it also hasn't been fully unified with other forces, like electromagnetism, or the weak and strong nuclear forces. And so the search continues. Why is this unification so hard? One reason is that quantum mechanics is probabilistic, while general relativity is deterministic. In quantum theory, particles can exist in multiple states at once until observed. In relativity, the curvature of space-time unfolds predictably from mass-energy distributions. Trying to apply quantum rules to curved space-time leads to mathematical chaos. Another reason is scale. Gravity is incredibly weak compared to other forces. You can lift a paperclip with a magnet, overcoming the entire gravitational pull of the Earth. To see quantum effects of gravity, we need to probe the Planck scale, where energies are so high that current technology can't reach them. But that hasn't stopped theorists. They've developed models of quantum black holes, predicted new particles, and even simulated baby universes forming from quantum foam. They've asked questions once reserved for philosophy. Is space-time fundamental or emergent? Are particles real or just vibrations of an underlying field? Is the universe deterministic, Or is it information all the way down? Some thinkers believe that information itself is the key. If black holes don't destroy information, a conclusion emerging from the resolution of the black hole information paradox, then perhaps information is more fundamental than space, time, or matter. This aligns with ideas like the holographic principle, which we discussed in the previous segment. In that view, the 3D universe is a projection of 2D information encoded on a cosmic boundary. A quantum gravity theory might then describe how this information behaves and how it gives rise to the world we experience. We're not there yet, but new tools are emerging. Advanced particle accelerators, gravitational wave detectors, quantum computing, and even simulations of quantum spacetime. And with them, new insights may arrive. What we know is this: the universe is not obliged to be simple, but it is, at every level, deeply interconnected. Gravity and quantum mechanics are not enemies. They are two sides of the same coin, waiting for us to decode the language that binds them. And when we do, it won't just explain black holes or the Big Bang. It may reveal what reality truly is, from its smallest spark to its grandest curve.